Hello, students. We are starting a new topic, circles. We actually started this at the end of the last chapter. The circle chapter has 5 sections. The first section is about arcs and sectors. So we're doing this today and tomorrow. And then we have something called tangents, which are different than the tangents in a right triangle. They're basically, if you have a circle, there's a line off of the circle. This is called a tangent line. It touches the circle at exactly one spot. Arcs are like that. Sectors are like slices of pizza. Some pepperoni on there. The next section in chapter 10 is about, let me double check my notes here. Oh, something called chords. The circle, this is a chord. It's a line segment. It has its endpoints on the circle. And then we have a section called inscribed angles. I put this on the final last year. Inscribed, I wonder what that means. And the last section with circles is called secant lines and segments. Secant lines. A secant line is if you have a circle, there's a line that goes through it, and sometimes there's another line that goes through it or is tangent to it. I kind of drew that bad. It's more often you'll see it like this. We'll try to figure out what those angles are using the circle. Inscribed angles are just what it sounds like. There's a circle, and inside the circle, I'm going to draw an angle. So this angle is inscribed. So today we're going to get in and talk about arcs. Arcs. So it's a new shape. Let's step back and talk about circles again. So what is a circle? A circle is a set of points equidistant from a center point. So there's a center point. Here is a distance. And if I draw a point there and then I spin this and I keep drawing points, it's a point next to a point, next to a point, next to a point, next to a point, next to a point. If I continue that, I've created a circle. So a circle is a set of points on a flat surface, on a plane, that are an equidistance from a center. One word that's important with circles is radius. And radius has 2 meanings. Or 2 kind of interpretations. If I say, hey, look at this picture, what's the radius? You could say, oh, the radius is line segment DE. Or, yeah, that's the name of the radius. It's a shape, it's a line segment. It's a piece of a line is a radius. You could also say, what's the radius? And if there was a number right there, you could say the radius is 2. Or the radius of circle D is 2. Let me jump back up here again. How do you name this circle? This is called circle A. So we use a capital letter for the name of the point. And then you draw a little circle, put a dot in the middle, and this says circle A. Circle A. That's how you would read that. Right, and another thing that's interesting to find on a circle is the circumference. Now, the circumference you can't name with letters. The circumference, when we ask you for circumference, we're actually looking for a number. And the number is how long it takes to get all the way around the circle. The circumference is a number that represents how far it is around the circle. So let's practice using the circumference formula. So first, let's look at our circle here, and what's the radius? How far are the purple points from the center of the circle. They are 2. Okay, 1, 2. So the radius of this circle is 2. The radius equals 2. And there's no points named here. So we would just say r equals 2. We always use a lowercase letter for radius. For circumference, we actually use an uppercase letter, c. And the circumference, there's 2 formulas, but the one we'll use is 2 pi r. And this came from the definition of pi. People for a long time figured out how many radii or how many diameter would it take to cover a circle. And if the circle is bigger, that means it's going to have a bigger diameter. And if the circle is smaller, it's going to have a smaller diameter. So that number that describes the relationship between those is called pi, which is just a Greek letter of the alphabet. Like if it was found, if they figured it out today, they might call it P or Q. So 2 pi r is our formula if I want to find the circumference. In this problem, the radius is also 2. So I don't always show this work, but I can rearrange the factors here because it's multiplication. I can change the order. That's called commutative property. You can switch the order. So a really good answer for this is 4 pi. There's no units on this, so we would just leave it like that. The circumference of the circle is 4 pi. So about 12 and a little bit to get all the way around. All right, here's our new shape for today. It's an arc. What is an arc? How do we write it? What is it about? Okay, this shape is an arc. It looks like this. What is it? It's, excuse me, part of a circle. We would actually never draw it separate from the circle, but this is the shape that we're looking at. Shape. The shape that's curved like that, that's AB. Okay. So if I was going to write about it, I would actually use this little curve or arc AB. And when I write that, I'm talking about arc AB. Arc AB is not a huge part of the whole circle. It's just this little part of it. So we would call this a minor arc. So arc AB is a minor arc. Arc AB is a minor arc. All right, what else? What else can we do with arcs? Is there another arc AB? We would actually never draw it this way, but just to show you. What if I went the other direction from A to B? What if I went from A all the way through and back to B? That's a really different arc. That's a bigger shape. That's a bigger portion of the circle. So if I was going to do arc ACB, that's the other way. That is a major arc. Arc ACB. If it's big, then you need all 3 letters. Because I don't know if you say arc AB, I'm not sure if you want me to go this way or this way. So a really good way to tell you, hey, I actually want the big one is to put another point on here. So arc ACB is a major arc. If point C was on the, oops, I want green. If point C was on the diameter, then I would have also this shape and this shape here. I think we use 3 letters. A, B, C is a semicircle. That's if That's if C was sort of on the diameter. If point C is in line with A and P, points A and P. Okay, so that's some things. What can we do with an arc? Well, we can measure it. And there are actually two ways to measure arcs. Because arcs are kind of related to angles. If I draw an angle, I put this little arc in the middle of it, right? So I can measure that distance. But an arc is also related to a line segment because an arc is part of a circle, right? And if I take this shape and I stretch it straight, if I pull it, like if it was a string and I pull it straight, I could think of it as being a length. So we can actually measure arcs two different ways. We can measure it in degrees, like an angle, or we can measure it as a length. So measure an arc like you would measure an angle, and measure the length like you would measure a segment. Now, if I ask you, let's draw what's called a central angle. So a central angle will come back again, but it's an angle that has its vertex at the center. The central angle of a circle is an angle formed by two radii. So here's a radii, and here's another radii. And it has the vertex at the center of the angle. I'm going to call it point H. Hello, circle H. Hello, central angle. Okay, and I could actually show you the rest of the angle. Our angle goes through like this. Angle H is a central angle because its vertex is on the center. Angle H is a central angle. Its vertex is on the center. And if I know the measure of this angle, then I know the measure of this arc. So the other way to measure the arc is by the length. And the length is going to be whatever part of the whole circle it is. We'll get to that. So if I ask you for the measure of the arc, that's the same as the measure of the central angle. So we can look at arc JM, and that number is going to be the same as the measure of this angle in here. Angle JPM is a central angle. It has its center at P. And so if I know the measure of this angle, then I know the measure of the arc. It's really, really straightforward. Also, arcs can be congruent, just like angles can be congruent. If angles have the same measure, they're congruent. If arcs have the same measure, they're congruent. And you can see the way we write it. We write it with the little m. So the measure of angle JPM is the same as the measure of arc JM. So let's do a problem. What's the measure of this minor arc AB? Well, it can't get too much easier. The measure of arc AB is simply 95 degrees. The measure of arc, this little minor arc AB, is 95 degrees. You barely have to show any work, okay? If you have a central angle and you have the measure of the central angle, that is the same as the measure of the arc. We will often write it out here next to the arc. And the way you read this is the measure of arc AB is 95 degrees. All right, is there another arc in this picture? How about what is the measure of the major arc, ACB? And how are we going to do that? If I know that this part's 95, how am I going to find the measure of this arc? Well, I need the measure of this central angle. So I need to find out how much that is to get from there to there. Any ideas? Yeah. You need to know that inside a circle is how many all the way around? 360. So if I want to find the measure of the major arc, and I know the measure of the minor arc, I'm just going to do 360 minus 95. Why? There are 360 degrees in a circle. So if I have part of it, I can find the major part of it by subtracting. So the math, if you do this math problem, you get 265. And if you wanted to know how to read that, you would say the measure of major arc ACB is 265 degrees. Measure of major arc, so big. Major if it's more than 180. Major arc ACB is 265 degrees. Woohoo! You could just write it like that. Okay, these are fun. I like working the circle. So I want to find the measure of all the arcs in here, and maybe all the central angles too. And I'm just going to go piece by piece. So what's the measure of arc AB? Well, AB is here. There's a 50 right in here. So the measure of arc AB is also 50 degrees because it's the same as its central angle. How about the measure of arc BC? How much is that? Well, there's a little marking here, and there's the same marking here. So guess what? They're congruent. This arcs can be congruent. Arc AB is congruent to arc BC, so they are both 50 degrees. Pay attention. How about the measure of arc AC? From A to C, how much is that? Well, you can add arcs together just the way you can add angles together. So it's the arc addition postulate. Arc AB plus arc BC is the same as arc AC. So it's 100. 50 and 50 is 100. How about the measure of arc CD? Well, here's C, here's D. And what angle measure is next to it? 90, it already gave it to us. But that means we also know this central angle in here is 90 degrees. Okay, so I could also write the 90 degrees in here. And going back, I could also write the 50 degrees in here. And totally work this circle. All right, let's do another one. What's the measure of arc BD? What's the measure of arc BD? How am I going to do that? Well, I'm going to go look. Here's B, here's D. So I want to know how big is it from here over to there if I'm measuring the arc. Well, the way to do that is to add 50 and 90. 50 and 90 together is 140. All right, now I'm kind of stuck. What's the measure of arc DE? How are we going to do that? Got to work for this one a little bit more. So I have these, I have this one. Oh, I have two missing, but they both have the same mark on it. So actually these two are the same. So how can I find, if I know all these, how can I find what's missing? Well, I know the total circle is 360. So I know 50 plus 50 plus 90 plus something plus 100 plus something is 360. Okay, I need to know what those somethings are. Another way to do it is do 360 minus 50 minus 50 minus 100 minus 90. Anyway, you'll find out that the leftover is, after I subtract everything off, is 70. So the two leftover pieces are 70. That makes sense. This is 360 minus 200, which is 160, and 160 minus 90 is 70. Okay, so both of these together are 70. So how much is each one? 35. Okay, which means what's the measure of arc DE? 35. Okay, we could keep doing this for a little bit more, but I'm going to move us on. Now let's talk about length. So we were talking about the measure of the arc. Now we're going to talk about the length of the arc. So that means I have this beautiful shape right here. I have a beautiful arc from F to G, and I want to see if I was an ant and I lived on this circle, how long would it take me to walk from F to G, or how far would it be? One way to think about that is to take this G and stretch it straight. Okay, so I want to know how long is that? I'm going to call it X. And if I pulled that, if it was a string and I pulled it straight, how long would that be? Well, in order to do that, I need to know, it's part of the circumference, right? The circumference is also, if you pull the whole circle straight, that's what it represents, the distance walking all the way around. So for this one, if I can find the circumference all the way around from F to F, then I can find just the length that I want. So do we have a formula for circumference? Yeah, we do. It's 2 pi r. We already did this problem. What's the radius? The radius is 2. So the circumference of this circle is 4 pi. All the way around the circle is 4 pi. But we don't want all the way around the circle. We only want part of it. We only want the length. We want the length of arc FG. And you have to write it like this. There's no shortcut way to write it. And we know that it's only part of the way around the circle. Can you guys see how much around the circle it is? How much of it is it out of the total? That's right, it's 1/4. It's 1/4 of the circumference. And the circumference in this problem is 4 pi. And that's really nice because 1/4 of 4 is 1. And so the answer to this problem is this is pi long. 3.14159. Okay, so the length of is basically we want 90 out of the 360. And in this problem, that's exactly 1/4. So I'm going to go 4 pi. No, I think I'll put circumference there. 90 out of 360 of circumference. Maybe I'll do circle E, the circumference of circle E. Okay, how about the length of FG on this one? I'll use red. Here's of arc FG. So here's arc FG. This is what we want. But we're going to take that and we're going to stretch it straight. So there's F and maybe there's G prime over there. If I pull this around this way, woo, and I want to know how long that is, I'm going to call that Y. Haha. And I know that the length of arc FG, well, it's a semicircle. It's halfway around this circle because 180 out of 360 is half the circle. So in this picture, the length of arc FG is exactly half the circumference, half 4 pi. On this problem, it is 2 pi. Okay. That kind of makes sense. It's twice as far around. Okay. So we have pi 2 pi, 3 pi, 4 pi. All the way around this circle is 4 pi. If I want 1/4 of it, that's pi. And this is 2 pi, 3 pi, 4 pi. Here's what this looks like. It's just another way to write it. So if we want to find the length of S, the arc length, or the length which we're naming S, it's a fraction of 360. The arc length is a piece of the total circumference. And this is the formula we were just kind of looking at. It's the measure of the angle over 360. It's the fraction of the circle that you want times the circumference. You could set it up as a proportion too. So arc length out of the circumference is equal to the arc measure out of 360. There's two ways to measure arc length. There's the way that we just went over, and then there's also an easier way to measure arc length. And that is if you know something about radians. And radians are interesting. Radians are a different way to measure angles. And in higher math, we actually use them quite a bit more. On calculators, you will often see a DEG and an RAD symbol. That is a conversion between counting the circles in degrees, in 360 degrees, or counting it as the number of radii. Radians is radii that fit around the circle. And for radians, let me move on that. I don't want to say something wrong. Okay, let's do the length of JK first. And we've been playing with this idea. So I'm just going to use the formula for this one, and I'm going to use this formula. So the length of JK is n over 360 times 2 pi r. So we're going to do the length of line segment JK is n out of 360 times 2 pi r. 2 pi r is the circumference. So in this problem, we know it's 110 degrees. So we're going to do 110 out of 360 times 2 times pi. Do we know what the radius is? Yep, we sure do. It's 8. And then we'll finish this up. From here, if you want to practice your fractions, it's a really good idea. Okay. And I will show you some of the fraction work. So I see this as 11 times 10, and I see this as 36 times 10. Okay. The 2 and the 8 I'm going to put next to each other, and those are in the numerator. And the pi is also in the numerator. Okay. Or we can put it next to the fraction. 10 divided by 10 is 1. Do you see any other places to make a 1 here? I do. You guys know what 8 is? Another way to think of 8 is 4 times 2. Another way to think of 36 is 4 times 9. This is really good for your brain, pulling numbers apart and putting them back together. If you can do this, you're on track to do really well. Okay. That is another 1. 4 divided by 4 is 1. So the best math answer for this is going to be 44 pi over 9. This is what you would see in a Algebra 2 pre-calc book for the answer. If you want to change that to a decimal, or if it asks you to put it to the nearest tenth, simply type this into Desmos and see what it says. If you want to push your brain a little bit, do some of this fraction work here. Yeah, and you could type this in and see if it matches if you type this in as a way to check your work. And we haven't really talked about units. A lot of the pure math that you do is not going to worry about units so much. But if this was a real life application, you would need to consider what units you were talking about. Okay, so the other way to measure lengths of arcs is with radians. I started to talk about that already. So let's see what a radian is. Let's see if we can understand this. How do you find mountain arc length? Besides degrees, angles can be measured in radians. Don't worry, you'll see this again in other math classes. A radian is equal to the measure of a central angle that intercepts an arc with length equal to the radius of the circle. So if this radius is the same length as this arc, and which is the same as this radius, right? Well, if all three of these are the same, then the measure of this angle is called 1 radian. It's 1 radius to get from here to here. Okay, it takes 1 radius for this circle to turn from this to here, from here to here. Okay. What that means is, if you are trying to do this in radians, it's really easy. Since the arc length r corresponds to 1 radian, there are 2 pi radians in a circle. There are 2 pi radians, so 2 pi is the same as 360, which means that all the way around a circle is 2 pi. Halfway around a circle is pi. A quarter of the way around the circle, I'm going to get rid of this. So if I was going to measure this in radians, this would be 1 pi. This would be pi over 2. 180 degrees is pi. And all the way through the middle of the circle is 2 pi. You will see this a lot more. We actually even graph things as units of radians. Well, let's see what this says. The length of the arc, to find the arc length, you can use this proportion. The variable theta, that's another Greek letter of the alphabet, is often used for angles measured in radians. So the arc length is what we're trying to find out of the total circumference is a fraction of the arc measured in radians over 2 pi, because the whole circle is 2 pi. The circumference is all the way around. The all the way around measured in radians is 2 pi. So if you do this fabulous math, you would, what they did here is cross products. No, actually what they did is they multiplied both sides by 2 pi r. And what happens here is 2 pi divided by 2 pi is 1. So it's one of the easiest formulas ever. You just multiply the radian degree measure, I said that wrong, the radian measure by the radius. So arc length is proportional to the radius, and theta is the constant of proportionality. To find the length of an arc measured in radians, all you have to do is multiply the two numbers that are given to you, the theta and the radius. So for this problem, this would not be 90. This would be pi over 2. If I wanted to find the length of arc FG, all I would do is I would do pi over 2 times 2, which is pi. Hey, we got that answer before, which is a really good thing. Because whether or not you measure it in using radians or degrees, you better get the same answer for the length. All right, so I said this was super easy. It is. Okay, all you need to do is you need to multiply this number by this number. So if I want to find the length of this beautiful major arc, XYZ, I'm just going to multiply the theta times the radius. And the theta is this weird number, 5 pi over 4. That's measured in radians, and then I just multiply it by 3. Okay. And there's no equivalent forms of 1 here. This 3 is like 3 over 1. The pi actually is up at the top, so this is 3 over 1, everything over 1. And I can just put it together. This is going to be 15, because with fractions, you multiply numerators, you multiply denominators. So this is 5 times 3 times pi, which is 15 pi. And this is 4 times 1 times 1, which is 4. This is the best answer for this problem. I think that's it. Woohoo! Fun times, radians. All right, be good, do your work, keep learning. Bye.